Welcome to Data Science in Context. My name is Mike Dakanbora, and this topic is computer vision. Computer vision as it pertains to facial recognition um, has to do with the Viola-Jones algorithm. This is the one that we'll be talking about today. It was created in 2001 by Paul Viola and Michael Jones, and as far as I understand, it's the first object detection framework to provide the detection rates in real time. And facial recognition was the motivator behind the algorithm's development. It's broken down into 4 steps. The first step is to use what's called Haar-like features. Alfred Haar was a mathematician from the early 1900s. He studied wavelets and light, but that's what this base is mostly based off of. What you have are edge features. You think of this almost like a 4-pixel structure. It could be more of a rectangle. You have line features and 4 rectangle features. What happens is the algorithm first takes your color picture and makes it grayscale. And then it analyzes the grayscale where it's valued from 0 is white and 1 is black. And then anything grayscale in between will slide on a scale depending how dark or light the pixel is. So for example here we have a human nose, and this is an edge feature in a rectangular shape, and it's running across every single set of pixels it can, and it approaches the nose right here. And as you can see, there's shadowing on one side due to the normal shadowing of the picture, and the light side on the left side of the nose. What's happening behind the scenes is the pixels are broken up in value. So you can see that the left half is much lighter in value than the right side, which is much more shadowed. And what simply is going to happen here is this entire side is going to be summed up and divided by pixel count, which is 16 here, and the same thing will happen for the white side. It gives us 2 values, and those are subtracted and given us a value. In this case is 0.4, or just over 0.4 at 402, which for this algorithm, it's good. Could be a good a positive detection for a potential facial feature. The second step here is the use of the integral image. I'm going to try to be quick here explaining this, but just how we just had 32 different pixels and using summing, there's 32 different calculations. When the rectangles get big, there could be hundreds of thousands or millions of calculations if we did it that way. So what happens with the integral image is it kind of takes a shortcut. In this case, you have the 25 here is the bottom right corner of the rest of the block. And once you take the entire image here, of whatever the block of pixels is, you have integral images for every addition. So this 235 is actually the sum of this entire piece. But the great thing about it is no matter now, however big a rectangle is, you'll only ever need 4 calculations to get the actual value of the rectangle. So this 65 is this sum here. You don't need 12 anymore, you only need 4, you don't need 1.5 million, you only need 4. And that makes things much more efficient. From there, the next step is you train the algorithm with a bunch of faces, a bunch of non-faces. And essentially what's happening here is it's a sum of its parts. Each classifier or feature of its own is weak, but together they're strong. And then what the AdaBoost training does is it gives more weight to the incorrect images. So what that does is it allows the next Haar-like feature to know the importance is higher, which increases the chance of it correcting itself. And lastly, the last step is cascading. What happens here is, for example, we have a rectangle or a square over a piece of the image, and instead of using all of the features, it will stop at the last feature that is good, that is detected within that rectangle. So for here we have an edge feature that's light and dark, which could be like the eyebrow, light and dark. We have a line feature, which could just be like the eye, light, dark, light. So that's good. And another line feature here, which could be similar, just like the eyebrow. So that's good. But then we have an edge feature here that doesn't fit anywhere. So this gets rejected down, and immediately this also gets, everything else gets rejected, and we say this rectangle has these three classifiers, then it moves on. So it's an efficiency thing. So with that being said, we'll use a practical application to show you, give you an idea what the classifier does. What we have here is, I'm using Python, it's the OpenCV platform, but basically you have, you load the cascades with XML, you can get that from University of Michigan, and you define the function, it's a detection function, you can also find this online. It's pretty, it's well sourced, as well as facial recognition for the webcam. And once you run these, you can see that hello all, it's detecting my face. It's actually, you can see the false images there too, right here on the bridge of my glasses. So if I took that off, it could be it's a little more accurate. But that's everything. That's the Viola-Jones algorithm at work and applied in Python. And that's that. So I hope you enjoyed this presentation, and I'll speak to you all soon.